So let me do an example, because I think an example will help clear some things up, and we'll discuss some of the equations and stuff. Let's say I tell you to find x in the equation below, x cubed is equal to 20. And I'll say using the bisection method. And I'll tell you that we'll assume that our initial guess is my xlow will be 1 and my xhigh is 4. And reminder, I don't know what these function values are when I plug in 1 and 4. Instead, I am saying that the lower number is the smaller of the x values, the one that's further to the left. The higher value is the one that's further to the right. Those are what we mean by low and high. Just think about the magnitude of the number. If it's very, very low, it's further to the left on the x-axis. If it's very high, it's further to the right. This has nothing to do with the function itself. The low and the high are just strictly telling us where x is. Okay, so we have x cubed is equal to 20. We're trying to find that root. We are not in the form of f of x is equal to 0. We need f of x is equal to 0. So to do that, I'm going to subtract 20 from both sides, and now I have f of x equal to 0. That's great. So I'm going to draw a picture, and it doesn't need to be perfect. Or rather, let's first figure out if our signs of xlow and xhigh, what they are, if they're positive or negative. So we'll plug in xlow. If I plug that in, I get 1 cubed minus 20. That is a negative number. And again, it's not going to equal 0. Those are the initial guesses. If it equaled 0, we did a really good job guessing. We'll plug in xhigh. It'll be 4 cubed minus 20. 4 cubed is 64 minus 20. This is a positive number. Basically saying that f of x low is less than 0. F of x high is greater than 0. I'm going to draw a little plot. I don't know what this function looks like perfectly. But all I know is that when I plug in 1, I'm going to get a negative number. And when I plug in 4, I'm going to get a positive number. That's all I know. That's all I really need to know. This line is so terrible. Sorry. There you go. A lot better. And I know that there has to be a root that's in between. So the first thing we're going to do is calculate our midpoint. So first find x mean. And the midpoint is just going to be the sum of the 2 points divided by 2. X low plus x high divided by 2. 1 plus 4 divided by 2. This ends up being 2.5. So that point is the one that I'm interested in. We now need to see what is the sign at 2.5 of the function, because depending on if it's positive or negative, it'll dictate what 2.5 becomes for our next iteration. So let's say that 2.5 was positive. We don't know yet, but let's pretend it's positive. Is it going to become the new x high or the new x low? Well, let's think. If I drew a line like this between 1 and 2.5, it looks like I'm passing through the point that we want, the root. So in this situation, the 2.5 is going to become the new x high. If we go ahead and say the 2.5 is going to be negative, if I drew the point between 1 and 2.5, we don't cross the x-axis. But if I go between 2.5 and 4, now I do. So in this situation, 2.5 becomes the new x low. It's replacing the 1, the old x low. So that's why we need to figure out what the sign is. So we'll say that f of 2.5 is going to be 2.5 cubed minus 20. If we go through that, this is negative 4.375. So that means that our x mean point is negative. So this is going to be our new x low. This is basically our first iteration. We've replaced our old point with a new point. So this 1 is basically done for us. Now I'm here with the 2.5 and the 4. So let's do iteration number 2. Find x mean. X mean is the new x low. And again, this function value is not the new x low. That's f of x. We don't care about that value. All we care about is the sign. This is going to be x low plus x high divided by 2. If we do that, we will get 3.25. So let's come into here and say, okay, now we're like at 3.25 right in the middle. Is that going to be the new x low or new x high? Well, it depends on the sign. If the sign was positive, what do you think that becomes? That becomes the new x high because it's going to replace the 4, and our window is now between 2.5 and 3.25. If f of 3.25 was negative, well, that would become the new x low because of the fact that we're bracketing the root in between a positive function value and a negative function value. You have to have opposite signs at the tails of that window. If the 4 is positive and the 3.25 is negative, that's our window. They're opposite signs. So we have to plug it in now. So now let's plug in f of 3.25. 3.25 cubed minus 20. And looking at that, this is 14.328, which is positive. Let's come back up here and draw where it's going to be. It's going to be right around here. Is that going to be our new x low or our new x high? Well, as I just said before, this is going to replace the 4. So this is our new x high. We'll go one more time just for practice. For iteration number 3, let's find the new x mean. X mean, that's going to be, if we come back here, and I can go ahead and draw a little, I like drawing this before, this idea of where our roots were. Originally, they were 2.5, 4, 3.25. We knew that at 2.5, this value was negative, at 4, it was positive, and this new one is positive. Again, when we plugged in 2.5, we got negative. When we did 4, we got positive, and 3.25 was positive. That means that this is our new window now. Our x mean is going to be 2.5 plus 3.25 divided by 2. That x mean now is going to be 2.875 right there. And if I wanted to just go ahead and think about what my next iteration would look like, we would ask, what would the 2.875 replace? We can plug in 2.875 into the function. If we do that, we also get a positive number. That means that this is positive, and then we would have another window in between 2.5 and 3.25. And if we went through this and found the relative approximate error between iterations, let me go ahead and make a table. Iteration, let's go ahead and summarize. X low, X high. What else do we got? X mean, and then epsilon A as a percentage. Iteration number 1, we said that the xlow and the xhigh were 1 and 4 respectively, and we found that our mean was 2.5. That's what we did at the first thing in the video. Now, depending on who you talk to, we usually think about this as being the first iteration, which means we wouldn't have a relative approximate error. Others might say that you can go ahead and reference that x mean to your original guess. Because at the end of the day, we're trying to find a root, and xlow and xhigh are guesses for what that root is. So you can go ahead and do our current approximation. Remember that this is current and is previous over current times 100%. I could do 2.5 minus 1 over 2.5 if I'd like. Or you could do 2.5 minus 4 over 2.5. It won't change the percentage because they're equidistant. It's right in the middle. I think you get 60% if you do this, or something like that. On our next iteration, we saw that x mean became the new xlow, so this became 2.5, and xhigh remained exactly the same. Our mean in that situation was 3.25. If we do 3.25 minus either one of those xhighs or xlows, that's the previous iteration, essentially, we will get 23.1% roughly. And then we did this one more time at the end, and this was something like 13.0%. Which doesn't bear a lot of confidence in our root. The true root in this problem is 2.7144. With that final guess, our relative true error was something like close to 5.9% or something like that. Which is fine. I mean, it's not awful, but it is just an approximation. And you would see that this is a very slow method. It would take a lot of time. And because of that, it's not necessarily preferred. However, there are advantages. This video is going over way longer than I expected it. Maybe I'll split it into two. Advantages. This is guaranteed to converge if we bracket a root at the beginning. Which means that we'll always get an answer. That's huge for us. Because if it brackets it, then that means we'll get closer and closer in each iteration. That's our first advantage. The second advantage is that we will get closer with each iteration. With each iteration, we get closer to the true value. There are some methods where you might end up passing the true value or going off course a little bit and then correcting itself later. But with this method, you're always zoning in on the target, which is our root, the thing that makes the equation true. That's a really good advantage. Disadvantages, though, it's very slow. It takes a long time to converge to the root. And that's, tedious. Another disadvantage is that it's very dependent on the initial guesses. And let me basically show you what I mean by that. If I have a function that looks something like this, and I choose an initial guess that gives us an f of x low there and an f of x high there, I see that they are the same sign. They're both positive in this example. Which means that I don't know if there's a root in between. Again, this blue function we might not know. I might just see these 2 points. And just from the knowledge of the bisection method, if I'm going to go ahead and connect these dots, perhaps it doesn't cross the axis. The prerequisite is that we have this function f of x equals 0 that we're looking for, that root. If the sign at your two initial guesses is the same, there's no guarantee you cross the axis. So that's not great for us in terms of that situation. Another thing that's very dependent on the initial guesses is how fast the method takes. In the previous example where I had the guesses of like 2.5 and 4, let's say it wasn't 2.5 and 4. Let me go ahead and make this really compact. Let's say it looks something like this. I do 2.5 and 100. Note the root is down here near 2.5. I think it was 2.7. Even though we're closer to the lower value, we don't know that. So that means we have to go through finding a new x mean, which will be in between them. Something like 50 or whatever it is. Then we have to do it again to get something around 20 something. And then again, and we have to have those extra iterations present because we started so far away from the original root. For the method to be faster, you need both roots or both guesses to be near the root. And it's not even that much faster in that case because you're still having to do this whole slow process of halving the window each time. Another disadvantage is that it won't work for all functions. When I say all functions, if the function doesn't have a root, then obviously it's not going to work. We're not interested in finding that root. But what I mean is there are functions with roots that we can't do this for. And a great example of that is something like y is equal to x squared. It is touching the x-axis at x equals 0, but we can't start the function because this function never goes negative. So it won't work for this. And the last issue that's a problem is if you have a singularity existing. When I say singularity, I mean something like 1 over x, where if x is 0, that's a problem. Why is that? This function 1 over x never touches the x-axis. It never touches the x-axis. Will you let me draw, please? Okay. 1 over x looks something like this. If I plug in very low x, we go towards infinity. And very big x, we approach 0. And vice versa. If I choose an xlow and an xhigh, those are opposite signs. We think bisection works, but it won't. We'll converge on the asymptote at x equals 0. We won't actually converge on any points because there are no points that cross the x-axis. So depending on the knowledge of your function and depending on how difficult the mathematics are, or any sort of singularities present or things like that, you may or may not want to do the bisection method. Newton-Raphson, as we'll see in the next video, is faster. It only requires one initial guess, but it's not guaranteed to converge like this is, and it has its own limitations that we'll talk about in the next video. If you have any questions, please let me know. Otherwise, I'll talk to you soon. Thanks so much for watching.